In the beginning, there is only silence. Not the silence of a quiet room, but the deep, eternal stillness of the cosmos. Out here, galaxies are not fixed points. They are ships, drifting endlessly across a cosmic ocean. And with every passing moment, they are sailing farther apart. The universe is breathing, and with every breath, the space between everything grows wider. For most of human history, we imagined the cosmos as unchanging, eternal, and still. Then we learned it was expanding. That was strange enough. But the real shock came when we discovered the truth. The expansion is not slowing down. It is speeding up. Something out there in the dark is pushing everything apart. A force we cannot see, cannot touch, and yet it shapes the fate of the universe. It is everywhere, filling the void between galaxies, driving them away from one another like leaves scattered in the wind. What is this force? Why does it exist? And what will it mean for the distant future, when galaxies vanish beyond the edge of sight, leaving the universe a cold, empty desert of stars? This is the mystery that has shaken physics to its core. A puzzle so vast that it challenges everything we thought we knew about space, time, and reality itself. Tonight, we dive into the dark heart of the cosmos to follow the invisible force that is tearing the universe apart and ask whether its secret might change our understanding of existence itself. If you are new here, join the journey. Like, subscribe, and let's begin. The story begins not in the late 20th century, but in the quiet dawn of modern cosmology, almost a century ago. At the time, the universe was believed to be eternal and static, a silent cathedral where the stars had always burned and always would. Gravity was imagined as the great architect holding everything together, keeping the heavens balanced in an eternal stillness. But in the 1920s, the astronomer Edwin Hubble stood at the giant Hooker telescope atop Mount Wilson in California and saw something that changed everything. Using the new technique of measuring Cepheid variable stars as cosmic mile markers, Hubble showed that many of the faint nebulae in the night sky were not clouds of gas within the Milky Way, but entire galaxies, island universes, each containing billions of stars. Then came the revelation that transformed human understanding forever. The light from those galaxies was redshifted, stretched toward longer wavelengths, as though the galaxies themselves were rushing away. The cosmos was not still. It was expanding. Space itself was growing, carrying galaxies with it like leaves on the surface of a rising tide. It was a discovery so profound that even Albert Einstein, who had earlier modified his equations to force a static universe, was compelled to abandon his so-called cosmological constant, a term he had inserted to counteract expansion. When Hubble's data reached him, Einstein reportedly called it the greatest blunder of his career. From that moment on, a new vision of the universe took hold. If space was expanding, then it must have been smaller in the past. This was the seed of the Big Bang Theory, the idea that the universe had a beginning, a moment when space and time themselves burst into being. And yet, there was an expectation built into this vision. The expansion might continue for billions of years, but it would not go on forever. Gravity, the slow, patient pull of all the matter in the universe, would eventually act as a brake, slowing the expansion, perhaps even reversing it one day, collapsing everything back into a big crunch. For decades, cosmologists debated how much matter the universe contained, and whether its density was great enough to stop the expansion, or too small to ever halt it. This quiet confidence lasted for most of the 20th century. Cosmologists believed that with better observations, they would simply measure how quickly the cosmic expansion was decelerating under the influence of gravity. The question was not if the expansion was slowing, only how much. Then came the 1990s, and with them a revolution no one expected. Two rival teams of astronomers set out to measure the universe's fate more precisely than ever before. The first was the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The second was the High-Z Supernova Search Team, led by Brian Schmidt and Adam Riess. These scientists turned their attention to one of nature's most reliable cosmic tools, type Ia supernovae, exploding white dwarf stars that flare with such uniform brightness that they serve as standard candles, allowing astronomers to calculate their distances with remarkable accuracy. The plan was elegant. Find supernovae in distant galaxies, measure their brightness and redshift, and plot how the expansion of the universe has changed over billions of years. These explosions would act as time capsules, allowing astronomers to glimpse the universe's expansion rate at earlier epochs. The expectation was clear. The supernovae would reveal a cosmos gradually slowing down, a universe pulling back against its own expansion. But when the data came in, the universe told a different story. Both teams, working independently, saw the same result. The supernovae were dimmer than they should have been, not because they were fainter, but because they were farther away than expected. This meant that the universe had expanded more than anyone predicted. The expansion was not slowing down, it was speeding up. This was a moment of scientific vertigo, something unseen, something woven into the very fabric of space-time, was driving the galaxies apart faster and faster. The quiet assumption that gravity would eventually reign in the expansion was shattered. A new and strange force, soon to be called dark energy, seemed to be overpowering the attractive pull of matter. The reactions of the scientists themselves were a mixture of astonishment and disbelief. Perlmutter and his team double-checked their data again and again, searching for systematic errors, anything that could explain the unexpected dimming. Schmidt's team did the same. But every check, every recalculation, only confirmed the result. It was as if the universe was whispering a secret it had hidden for billions of years. In 1998, both teams published their results, and the cosmic paradigm shifted overnight. The announcement stunned the scientific community. Cosmology was no longer about measuring how much the universe's expansion was decelerating. It was about understanding why it was accelerating at all. Three men stood at the heart of this revelation: Saul Perlmutter, Adam Riess, and Brian Schmidt. Their combined work earned them the 2011 Nobel Prize in Physics. But more than that, it opened a new frontier of mystery. By revealing the accelerating universe, they had also revealed that nearly 70% of the cosmos is made of something unknown, something invisible, a form of energy that fills all of space and drives it apart. The first whispers of this cosmic force echoed like a challenge to human reason. It was not enough to know that dark energy existed. The question was why? Why does the universe have this property? Why is the strength of this mysterious energy just enough to begin dominating now, billions of years after the Big Bang? And what destiny does it set for everything that will ever exist? This was the dawn of a new era in cosmology, one in which every telescope, every satellite, every experiment would be turned toward a single haunting question. The discovery of the accelerating universe was not the end of a story. It was the opening of a door into a mystery far deeper than anyone had dared to imagine. The announcement of an accelerating universe landed like thunder on the quiet ground of 20th century physics. For decades, cosmology had walked a steady, almost reassuring path. The expansion discovered by Hubble was dramatic, yes, but it was predictable. The universe was imagined as a great clockwork, set into motion by the Big Bang, gradually slowing under the pull of its own gravity. It was a picture that allowed for certainty. One could calculate the density of matter, project the fate of all things, and imagine a cosmic future either collapsing in fire or drifting to a quiet freeze. But the supernova measurements overturned that vision in a single stroke. The galaxies were not merely coasting outward. They were speeding up, as though some hidden hand had taken hold of space-time itself and begun to pull it apart with ever-growing force. This was not just surprising, it was deeply unsettling. The shock reverberated all the way back to Einstein's general theory of relativity. In 1915, when Einstein completed his great set of equations describing gravity as the curvature of space-time, he was troubled to find that his solutions did not describe a static universe. His mathematics predicted that space must either expand or contract, but at the time, most physicists, including Einstein, believed the cosmos was eternal and unchanging. To reconcile theory with expectation, he added a term to his equations, the cosmological constant, a kind of repulsive pressure that exactly balanced gravity's pull and held the universe in place. Years later, when Hubble's observations revealed the universe was expanding after all, Einstein abandoned the cosmological constant. He reportedly called it the greatest blunder of his career. The equations without it were elegant, natural, and seemed to describe the universe perfectly well. Now, decades later, the accelerating expansion seemed to demand that Einstein's discarded term be brought back, not as a mistake, but as a clue. The cosmological constant had returned, like a ghost haunting modern physics, hinting that empty space itself might possess an energy that pushes everything apart. This was not merely a mathematical curiosity. It implied something extraordinary, that the vacuum, what we casually call nothing, was not empty at all, but alive with energy, seething with a force capable of driving the cosmos apart. It was a revelation that struck at the heart of physics, where space had always been seen as the neutral stage on which matter and energy performed their dance. Now the stage itself had joined the play, and if this energy was real, if it filled the fabric of reality everywhere, then it dominated the fate of the cosmos. Matter and radiation, the stars and galaxies, were suddenly demoted to mere actors in a story whose ending would be written by something invisible, something that no one had ever directly detected. For scientists, this was more than puzzling. It was almost unnerving. The balance of the universe had shifted under their feet. All of human history, all of science, had unfolded in an epoch where this mysterious energy was just beginning to dominate. It raised questions that felt almost conspiratorial. Why now? Why, in this tiny sliver of cosmic time, do we live in an age when the universe is accelerating? Why was the strength of this force so precisely tuned? Strong enough to overcome gravity, yet delicate enough not to have torn the cosmos apart long ago. This is what made the discovery feel less like a triumph and more like a confrontation with something vast and unknown. It shattered the comfort of a universe ruled only by gravity and matter, a cosmos that could be understood by weighing stars and measuring their motion. It suggested that most of reality was hidden, and that what we can see, the glowing galaxies, the clusters, the great filaments of matter, are only a faint scaffolding draped over an invisible engine. The emotional weight of this realization cannot be overstated. For generations, scientists had worked to make the universe intelligible, to write down equations that could predict its every motion. And just when the picture seemed nearly complete, the cosmos revealed that the greatest part of itself was still a mystery. The very expansion of space had turned wild. In the months and years following the supernova discoveries, physicists struggled to absorb the implications. Some argued for caution. Perhaps the data were flawed. Perhaps there were systematic errors in the way distant supernovae behaved. Others pointed to possible astrophysical explanations. Maybe dust was dimming the light, making the explosions seem farther than they were. But with every new observation, every cross-check from different teams and different telescopes, the result held. And as the reality of an accelerating cosmos sank in, it brought with it a strange existential shiver. The universe was not just expanding, it was rushing away, faster with every heartbeat of cosmic time. The great web of galaxies, the shining architecture of the observable universe, would not remain as it was. Over billions of years, more and more galaxies would cross the cosmic horizon, receding faster than light, vanishing from view forever. The night sky would thin, the cosmos would grow more lonely. This was the true shock of discovery. Not merely that the equations had changed, but that the future itself had been rewritten. The universe was no longer a place where gravity reigned supreme. A new unseen monarch had claimed the throne, a monarch with no name other than dark energy. And so a new era began. Physicists faced not just a problem to solve, but a confrontation with the limits of human understanding. If this invisible energy was real, it was unlike anything in the known laws of physics. It did not clump like matter, did not shine like radiation. It acted on the universe as a whole, as if it were the breath of the cosmos itself. The discovery had opened not a window, but a void, a vast, unanswered question hanging over all of science. The comfortable, predictable universe of the past had slipped away, leaving behind a cosmos that was stranger, more dynamic, and more fragile than anyone had imagined. The discovery of cosmic acceleration did not immediately become a celebrated fact. It became a challenge, one so unsettling that scientists could not simply accept it at face value. The first step was to question everything. The data, the methods, the assumptions. All of it had to be put under a microscope. Astronomers returned to the supernova measurements with forensic precision. They re-examined the light curves, recalibrated the brightness standards, and searched for every possible source of error. Could intergalactic dust have dimmed the distant supernovae just enough to mimic acceleration? Could some unknown evolution in the nature of these stellar explosions have fooled the measurements? For years, the two rival teams worked separately and together, checking their results against new discoveries. More supernovae were found, in greater numbers, and with better detectors. Each new observation told the same story. The universe was expanding faster than gravity could explain. The result was too consistent to ignore. It was no longer a statistical fluke. The cosmos was indeed being pushed apart by some invisible hand. Once the supernova data held, cosmologists turned to other tools, searching for independent confirmation. They found it in the faint afterglow of the Big Bang, the cosmic microwave background. This radiation, first discovered in 1965, is a relic of the time when the universe was only 380,000 years old. Its pattern, frozen in space like a baby picture of the cosmos, contains subtle ripples, tiny variations in temperature that trace the density fluctuations from which galaxies would one day grow. In the early 2000s, NASA's Wilkinson Microwave Anisotropy Probe, WMAP, mapped these ripples across the entire sky with unprecedented clarity. Later, the European Space Agency's Planck satellite pushed the measurements even further, giving humanity its most precise image of the early universe. The data spoke clearly. The geometry of space is astonishingly flat on cosmic scales. This meant that the total energy content of the universe must be very close to a critical value. Yet the amount of visible matter and even invisible dark matter could account for only about 30% of that energy budget. The remaining 70% had to be something else. Something smooth. Something that did not clump into stars and galaxies. The numbers agreed with what the supernova teams had seen. This was the moment when the term dark energy became more than a placeholder. It became a measurable part of the cosmic recipe. It was no longer just a possibility. It was required for the universe to look the way it does. But science did not stop there. Another line of evidence soon emerged from the large-scale distribution of galaxies themselves. Over billions of years, the sound waves that once rippled through the primordial plasma of the early universe had left a faint imprint, a preferred scale in the way galaxies cluster together. This feature, called baryon acoustic oscillations, acts as a kind of cosmic yardstick, a ruler stretched across the universe. The Sloan Digital Sky Survey, one of the largest mapping projects in astronomical history, measured the positions of millions of galaxies to detect this imprint. The results were astonishingly consistent with an accelerating expansion. This was a second, independent ruler, confirming the same conclusion. The universe's growth is speeding up, driven by something that behaves like a repulsive energy permeating all of space. As the evidence accumulated, the picture of the cosmos grew at once clearer and more disturbing. Roughly 5% of the universe is made of ordinary matter, the atoms that form stars, planets, and human life. Another 25% is dark matter, unseen, but detectable by its gravitational pull. The remaining 70%, the dominant ingredient of existence, is dark energy. In other words, the universe we see, touch, and measure directly is only a small fraction of what actually exists. This realization sent a chill through the world of cosmology. It meant that everything familiar, from galaxies to the glow of starlight, is merely a trace of reality. The true engine of the cosmos is hidden, silent, and almost unimaginably vast. Even as the big picture came into focus, new tensions began to emerge. One of them lay in the measurement of the Hubble constant, the rate at which the universe is expanding today. When measured using the early universe data from Planck, the value comes out lower than when measured using nearby supernovae and Cepheid stars. The difference is small but significant, and it has persisted despite years of refinement. Some researchers wonder if this Hubble tension is a statistical oddity. Others suspect it might be a clue that something is missing from our understanding of cosmic evolution. This puzzle only deepened the sense of mystery. If the expansion rate is slightly different depending on which cosmic clock one consults, then perhaps dark energy is not constant after all. Perhaps it is evolving, changing its strength over time, as if the universe is breathing more forcefully with each passing eon. What is most haunting is that dark energy does not simply push on galaxies, it pushes on space itself, causing the very metric of the universe to grow. There is no way to turn it off. Its influence is not local but global, acting everywhere, all at once. The deeper scientists looked, the stranger the picture became. By the early 2010s, dark energy had gone from a speculative curiosity to the dominant theme of modern cosmology. Conferences were dedicated to it. Observatories were built to measure it. Theoretical physicists struggled to reconcile its properties with quantum field theory, which predicts a vacuum energy density far larger than what is observed, larger by a factor of 10 to the power of 120, the most embarrassing mismatch between theory and observation in the history of science. This mismatch is not a small detail. It is a signal that something profound is missing from the human picture of reality. Either quantum theory is incomplete, general relativity needs modification, or the universe is stranger than any current model allows. And so the investigation continued, each experiment adding a new layer to the mystery. NASA and ESA planned next-generation missions, the Euclid Space Telescope and the Nancy Grace Roman Space Telescope, to map the expansion with exquisite precision. The Vera C. Rubin Observatory prepared to survey billions of galaxies, measuring how cosmic structures grow under the competing influences of gravity and dark energy. Every new measurement brings humanity closer to an answer, but also to a deeper confrontation with the nature of existence. If dark energy remains constant, it will eventually push every distant galaxy beyond reach, leaving the night sky nearly empty. If it grows stronger, the future could be even more catastrophic, ending in a big rip, where the expansion becomes so violent that galaxy clusters, stars, planets, and even atoms themselves are torn apart. This is what terrifies cosmologists. Not the end itself, but the possibility that the universe is writing its destiny with an energy we cannot yet name. The investigation that began with a handful of distant supernovae has revealed that humanity lives in a cosmos dominated by a force we do not understand, one that will decide how the story of time itself will end. The discovery of dark energy was not an ending. It was an opening, a widening of the cosmic abyss. If 70% of the universe is driven by a force no one understands, then the ultimate fate of everything depends on it. The question is no longer whether the universe will expand forever, but how. In the silence of the night sky, the answer is written in the future. If dark energy remains constant, the universe will continue to grow colder and emptier. Galaxies will drift away until only the nearest remain visible. Stars will exhaust their fuel one by one, leaving behind only white dwarfs, neutron stars, and black holes. Even these remnants will fade as they radiate away their last heat. Trillions of years from now, the cosmos will approach a state of maximum entropy, a final stillness called heat death. The universe will not end in fire, but in frost, as time itself loses all meaning in a sea of endless darkness. But this is only one possibility. If dark energy's strength is not perfectly constant, if it is even slightly stronger than a simple cosmological constant, then the future becomes far more violent. In this scenario, known as the phantom energy model, the expansion accelerates without limit. There comes a moment when distant galaxies are receding faster than light, disappearing from view. Then galaxy clusters themselves are torn apart. Later, stars are ripped from their orbits, planets unbound, and eventually the very atoms of matter are stretched until they can no longer hold together. This is the Big Rip, a cosmic dismemberment, the ultimate triumph of expansion over every binding force. No one knows which path the universe has chosen. The data we have so far suggests that dark energy behaves like a cosmological constant, unchanging, steady, eternal. But the margin of uncertainty is large enough to leave room for a more complicated truth. Each new measurement of the equation of state, the ratio of dark energy's pressure to its density, narrows the possibilities, but the question remains open. And then, there is the Hubble tension. The universe seems to give two different answers when asked how fast it is expanding. One answer comes from the early universe, from the cosmic microwave background, measured with exquisite precision by the Planck satellite. The other comes from the late universe, from supernovae and Cepheid stars in nearby galaxies. The two numbers should match. They do not. The difference is small but stubborn. and it refuses to vanish even as the measurements grow more precise. Some believe this tension is simply a reflection of unaccounted for errors, a quirk that will fade as techniques improve. Others whisper that it may be a sign of new physics, that something fundamental about the way the universe evolved between its birth and the present day is not fully understood. Perhaps dark energy was weaker in the past and is growing stronger. Perhaps gravity itself behaves differently on cosmic scales than Einstein's equations suggest. Perhaps there are hidden particles, invisible fields, or entirely new ingredients in the cosmic recipe. Each hypothesis is an invitation to imagine a reality stranger than the one humanity has grown accustomed to. The deeper cosmologists dig, the more the ground seems to shift beneath them. What was once a solid, predictable universe is now a landscape of uncertainty. The emotional weight of this realization is immense. For centuries, the story of science was one of convergence, of moving toward a single, unified picture of reality. Dark energy shattered that dream. Instead of closing the book on the cosmos, it tore out the final chapter and left blank pages in its place. This is what makes the mystery so haunting. The universe is not merely expanding, it is accelerating as though fleeing from itself. Space-time is not passive but restless, imbued with a tension that drives it apart. The more the expansion is studied, the more it resembles a force of destiny, a cosmic command written into the very structure of reality, and humanity is caught within it, unable to escape, unable even to predict where it leads. The galaxies may continue to drift away gently, leaving future astronomers marooned on an island of darkness. Or the expansion may quicken until everything, even the smallest particle, is torn into nothingness. Between these two fates lies every possible ending, and at present, there is no way to know which is true. The search for answers is relentless. Observatories on mountaintops and satellites in space are devoted to measuring the expansion with ever finer precision. They chart the clustering of galaxies, the bending of light by gravity, the faint glow of ancient radiation. Each new dataset is a clue, a fragment of a puzzle so large it spans the whole of existence. But with every discovery comes a deeper unease. The cosmos seems to resist full comprehension, as though guarding its final secret. Even if dark energy is mapped, measured, and named, there remains the deeper question of why it exists at all. What is this energy that fills the void? Is it truly constant? Or is it a shadow cast by some deeper dimension, some hidden layer of reality beyond what human senses and instruments can reach? This is the escalation of the mystery. Humanity has learned that it lives in a universe that will not stay still, that the very stage on which history unfolds is stretching beneath its feet. It has learned that the visible world, the stars, the galaxies, the light of the Milky Way, is only a fleeting arrangement, destined to dissolve in the face of an unstoppable expansion. The more that is learned, the smaller the known world becomes. The more precise the measurements, the more the universe seems to retreat into strangeness. And in this retreat lies the greatest challenge science has ever faced: to explain not just what the universe is doing, but why. The numbers do not lie. The universe is accelerating. Something unseen is pushing on the fabric of reality, and its influence is so vast that it accounts for nearly 70% of all energy in existence. And yet no one knows what it is. The first and simplest explanation is a return to an old idea, the cosmological constant. When Einstein first wrote his field equations of general relativity, they suggested that the universe should either expand or contract. But in 1917, astronomers had no evidence for either, so Einstein added a term, a subtle modification, to keep the universe static. When Hubble later discovered that galaxies were indeed receding from one another, Einstein reportedly called this constant his greatest blunder. And yet, decades later, this discarded term has been resurrected. Perhaps empty space itself is not truly empty, but infused with energy, a vacuum energy that pushes outward on the fabric of space-time. The mathematics of relativity allows such a term, and if its value is small and constant, it would drive precisely the kind of steady acceleration we now observe. But here lies the most unsettling twist. If this vacuum energy is truly a property of the quantum fields that fill the void, then the predicted value, calculated from quantum field theory, should be vastly larger, not by a factor of 2 or 10 or even 1,000, but by an almost unimaginable amount, one followed by 120 zeros. If that were true, the universe would have blown itself apart in the instant after its birth, Instead, it expands so slowly that galaxies can form, stars can shine, and life can emerge. This mismatch between theory and observation is sometimes called the worst theoretical prediction in physics. It is not just a discrepancy, it is a cosmic scream that something in our understanding is fundamentally wrong. If the cosmological constant is not the answer, perhaps the force is not constant at all. One idea is quintessence, a hypothetical scalar field that permeates the cosmos, slowly changing over time. Unlike a fixed cosmological constant, quintessence could grow stronger or weaker, shaping the past and future of cosmic expansion in ways that cannot yet be predicted. If it is real, its behavior could decide whether the universe faces a gentle fade into darkness or a catastrophic end in the Big Rip. Others take the mystery as a challenge to the very foundations of gravity. Perhaps Einstein's equations, magnificent though they are incomplete. There are theories of modified gravity, from FR gravity to massive gravity models, that attempt to reproduce the observed acceleration without invoking an unknown energy component at all. In these scenarios, it is not some new energy that is driving the expansion, but a subtle change in the way space and time themselves respond to matter. Still more daring are those who look beyond our universe entirely. Some physicists propose that what we call dark energy may be an emergent property of a deeper reality, perhaps the result of interactions with other regions of a multiverse. In this view, our universe is only one bubble in a vast cosmic foam, each bubble with its own laws, its own constants, its own fate. We happen to live in a region where dark energy is small enough to allow galaxies to form, and therefore small enough for observers to exist. This line of thinking leads to the anthropic principle, the idea that the universe is the way it is precisely because, if it were any different, we would not be here to notice it. Such reasoning is unsettling. It suggests that the cosmos is not fine-tuned for life by design, but that life exists only in those rare regions of a far larger reality where conditions are just right. We find ourselves in a quiet, balanced universe, not because it was made for us, but because no one could exist in any of the other universes where it was not. There are even bolder speculations. Some theorists suggest that dark energy may be linked to the energy of quantum fluctuations of space-time itself, that at the smallest scales, space is not smooth but seething, bubbling with virtual particles that flicker in and out of existence. Perhaps the large-scale acceleration we observe is the faint, distant echo of this quantum chaos. Each of these ideas opens a door to a new picture of reality. None have been confirmed, none can yet be ruled out, and behind each theory lies a philosophical question that no equation can answer. Why now? The acceleration of the universe began only a few billion years ago, roughly the same epoch in which stars like the Sun had time to forge heavy elements, and planets had time to form, and life had time to evolve. Had dark energy been much stronger, galaxies would never have formed. Had it been much weaker, the universe might have collapsed before life could begin. Somehow, in this vast cosmic lottery, we exist at precisely the moment when the acceleration is neither too weak to notice, nor too strong to destroy. This strange coincidence has been called the why now problem, and it is among the most profound riddles in cosmology. It invites a reflection that borders on the spiritual. Are we witnesses to a unique cosmic moment, a fleeting balance between creation and dissolution? Or is this simply an accident of perspective? That conscious beings can only exist in universes where conditions happen to permit them. The search for answers pushes physicists to the limits of imagination. They design new instruments, launch new satellites, and collect new data in an effort to pin down the nature of dark energy. But no matter how precise the measurements become, there remains the haunting possibility that dark energy is not a puzzle to be solved, but a window into something forever beyond human comprehension, a hint that the deepest truths about existence lie in realms where mathematics itself begins to fail. This is the stage of cosmology where science brushes against philosophy, where the pursuit of knowledge becomes inseparable from the confrontation with mystery. The accelerating universe is not just a physical phenomenon. It is a mirror in which humanity glimpses its own fragility, its own fleeting place in an ever-changing cosmos. The theories are bold, the equations elegant, the simulations beautiful. But at the heart of it all remains a simple, almost childlike question. Why is there something instead of nothing? And why is that something rushing away from itself, faster and faster, as though driven by a secret we are only just beginning to suspect? The mystery of dark energy is not a quiet puzzle left to philosophers. It is a call to action, and humanity has answered with an effort that spans the globe, the heavens, and the future itself. If the universe is accelerating, then the only way to understand it is to measure it, to trace its history, to weigh the invisible, to chart the unseen currents of space and time. Across mountaintops and deserts, on continents and in orbit, humanity has built machines of extraordinary ambition, instruments designed not to look at a single star or galaxy, but to map billions of them. These are not mere telescopes, they are time machines, revealing how the expansion of the universe has unfolded across cosmic history. On a high peak in Chile, under skies so dark that the Milky Way burns like fire, the Vera C. Rubin Observatory is nearing completion. Its legacy survey of space and time, LSST, will take a digital photograph of the entire visible sky every few nights, building a film strip of the changing cosmos. Over 10 years, it will capture the positions and brightness of billions of galaxies, allowing scientists to measure how they cluster, how they shear and bend light, how they drift apart. In those patterns lie the fingerprints of dark energy. Far beyond the Earth, the European Space Agency's Euclid mission is already at work. Sweeping its gaze across deep space with exquisite precision, Euclid is designed to chart the geometry of the universe, to create a three-dimensional map of cosmic structure stretching back 10 billion years. By comparing the distribution of galaxies across time, scientists hope to learn whether the acceleration is truly constant, or whether it has changed as the universe has aged. Soon, Euclid will be joined by NASA's Nancy Grace Roman Space Telescope, an observatory built to be the most powerful tool yet for studying dark energy. Roman's wide-field view will capture entire swathes of sky at once, measuring the subtle distortion of light caused by dark matter and the faint signals that reveal the expansion history of the cosmos. Together, Euclid and Roman will provide a stereo vision of cosmic evolution, an unprecedented dataset that will test every theory, from the cosmological constant to quintessence to modifications of gravity itself. But the search does not end with light. Astronomers are beginning to use an entirely new messenger, gravitational waves. These ripples in space-time, produced by the collisions of black holes and neutron stars, carry information about distance and time. By comparing the gravitational wave signals with their electromagnetic counterparts, the light from the same cosmic event, scientists can measure the expansion rate of the universe in a completely independent way. These standard sirens may one day resolve the Hubble tension and reveal whether the early and late universe are truly telling the same story. Other experiments probe the very nature of reality itself, testing whether the fundamental constants of nature, the speed of light, the strength of gravity, the charge of the electron, have remained unchanged over cosmic history. If even one of these numbers drifts, even slightly, it could point to a connection between dark energy and the deep structure of the quantum world. The effort is staggering. Hundreds of scientists, engineers, and programmers work together across nations and disciplines, driven by the same haunting question: what is tearing the cosmos apart? The scale of these projects reflects the scale of the mystery. Gigantic mirrors are ground to atom-level smoothness, detectors cooled to near absolute zero, data pipelines built to handle petabytes of starlight. All of it is in pursuit of something that cannot be touched, cannot be seen, and may never be fully understood. There is something deeply human about this endeavor. For as long as people have looked up, the stars have seemed eternal, unchanging. Now they are known to be receding, slipping toward a horizon from which they will never return. The work of Euclid, Rubin, Roman, and countless other surveys is an act of defiance, an attempt to measure the universe before it drifts beyond reach, to write down its story before the last light fades. And in this work there is hope. Each new telescope is not just a machine, but a question cast into the void. Each survey is a dialogue with the cosmos, asking what it is made of, where it is going, and why it is accelerating. Each answer brings the mystery into sharper focus, even as it grows more profound. Perhaps the data will confirm that dark energy is truly constant, that the universe is destined for a slow and quiet death. Perhaps it will reveal that the force is growing stronger, heralding a more violent end. Or perhaps it will show something no one has imagined, something that rewrites the laws of physics altogether. For now, the work continues. Night after night, images stream down from mountaintop observatories and space-borne telescopes. They are sifted, analyzed, compared to models, cross-checked against simulations. It is patient work, and it may take decades, but each step brings humanity closer to an answer, or at least to a better question. This is what it means to weigh the invisible, to measure the unmeasurable, to build instruments that turn silence into data, emptiness into numbers, and numbers into a glimpse of the ultimate fate of all things. In this pursuit, the cosmos is no longer a passive backdrop, but a partner in conversation. It answers not in words, but in patterns of light, in the whisper of gravitational waves, in the slow dance of galaxies across billions of years. It is up to humanity to listen carefully, to decode its meaning, to understand what story it is trying to tell. And so, the hunt for dark energy becomes not just a scientific mission, but a philosophical one. A search for humanity's place in a universe that refuses to stay still. The tools grow more powerful, the maps more detailed, but the central mystery remains. Why is space itself pushing everything apart? And what does that mean for the future of all who dwell within it? There comes a moment when the science gives way to silence, when numbers and equations are no longer enough and only reflection remains. The discovery of cosmic acceleration is not just a measurement, it is a message written across the sky, telling us that the universe we inhabit is far more restless, far more mysterious than anyone ever imagined. For countless generations, the night sky was a constant. The stars seemed eternal, unchanging, infinite. But now, it is known that the stars are not fixed, that they are drifting away, one by one, toward a horizon from which they will never return. In some distant age, billions of years from now, the galaxies will slip beyond the reach of light itself. The cosmos will grow darker, lonelier, until the Milky Way stands alone in an empty night. Future civilizations may never know there were other galaxies at all. This is not just a scientific forecast. It is a tragedy written into the fabric of reality, a slow erasure of the story of the universe. And yet there is a strange beauty in it, for this is the moment in cosmic history when the universe is still bright enough to reveal its secrets. This is the moment when the sky is still full of clues, when light from the first stars still washes over the earth, when the entire history of creation is still within view. The acceleration of the universe raises a question deeper than any equation. Does the cosmos have a destiny, or is destiny merely a word invented by minds longing for order? Perhaps the universe is not moving toward an ending at all, but simply continuing to be what it has always been, an unfolding, a becoming, a river with no mouth and no shore. If dark energy is truly a property of the vacuum, then every cubic meter of empty space is alive with a quiet force, a tension that holds the universe open. Without it, space might have collapsed back into nothing, or expanded too quickly for galaxies to form. Dark energy may be the reason the universe lasts long enough for life to arise, the invisible hand that keeps existence itself possible. In this light, the accelerating expansion is not only a source of dread, it is also a kind of grace. The same force that will one day scatter the stars is the force that allowed the stars to exist in the first place. It is the quiet current beneath all of history, carrying galaxies, planets, and living beings along on its endless flow. So humanity stands here, in this fleeting era, looking back toward the Big Bang and forward toward a future that may never be seen. The universe is not static. It is not safe. It is a vast and unstoppable motion. And we are part of that motion, carried on a river of dark energy into a destiny beyond imagination. Perhaps the final mystery is not whether the universe is expanding, but why anything exists to expand at all. Perhaps the force tearing the cosmos apart is the same force that holds reality together. And so the story closes not with an answer, but with a question, whispered into the infinite night. What if the dark energy that pulls the galaxies away is the very breath of existence, the pulse that keeps the universe alive?